All right, so we've implemented the basics of a hash table. We have a way of inserting, we have a way of retrieving a value. We also did the keys and values methods, which aren't as important, to be honest. Now let's talk about the big O, the time complexity in particular, of these basic operations. So insertion, deletion, and accessing data on average, and also best case, are O of 1, constant time, which is fantastic. That's great. And this really comes down to how good your hash function is. One, how fast the hash function itself is, and two, how evenly it distributes things. Minimize the number of collisions. Now remember that big O is a simplification of things. We remove constants, we simplify whenever possible. So saying that our time complexity is O of 1 for insertion doesn't mean that there's only one operation that it takes to insert. It just means the general trend. So it is possible to write a good hash function that is constant time, and pretty much every programming language that has an implementation of a hash table has a constant time hash function. Now that's different than a cryptographic hash function, which does need to actually run for every single bit of data as an input grows. Let's say a file grows from 1 megabyte to 200 megabytes. The hash function needs to actually traverse or parse every piece of that data if it's a cryptographically secure hash function. But when we're talking about hash tables, it's okay if we only look at part of the data, only part of the string in our case, which is what we did. So it's possible to write, in general, a constant time hash function. So insertion, deletion, and access, in general, average case, best case, are constant. So if we had a good hash function, and this is our data set visualized where this is showing, one piece of data stored here. This is talking about separate chaining. So we have, certain indices have two pieces. Even if it takes us one operation to hash our data, let's say we're accessing something like we're accessing this value here. So I have to first hash the key. Then it tells me index 9. I go to index 9. Well, there's two pieces here, so I have to go look at the first one and then the second one. And overall, we would still say that it is constant time because it's 3 operations every time or 5 operations every time. But if we grew this to be 10,000 items or 20,000 elements in our hash table, we would expect it to, with a good hash function, be evenly distributed. It is possible that we could have a really bad hash function that distributes everything really unevenly, everything into one index, which would be pretty useless. But if this was the case, if I wanted to retrieve, or if I wanted to insert, if I wanted to delete something from the end, it's going to be O of n time, because even if my hash function itself is constant time, if it's distributing everything into one spot, then it's basically just a list. And to insert at the end of a list is O of n. It's linear time. So it really comes down to how good your hash function is, how fast it is itself, but also how evenly it distributes things. And this is why I don't recommend writing your own hash functions. Use ones that are known, that are implemented by other languages. There's lots of libraries online. So if you do have to do that, I recommend using something that someone else has already done. So in general, when we talk about hash tables, they're very, very fast. O of 1, constant time for insertion, deletion, and accessing. And when I say access, that means using a given key, finding the corresponding value. When we talk about searching, well, for searching for a key, it can still be very fast. It can be constant time. But if we are searching for a value, then we need to go through every single thing, every item, and check. So that would be O of n. All right. So that's a big O in general, time complexity for hash tables. Now let's do a quick recap. So hash tables are collections of key value pairs. Cool. They exist in many languages. They're already implemented. Dictionaries in Python. They're similar to objects, or actually closer to maps in JavaScript. Pretty much every language has an implementation. So hash tables can find values very quickly using a key. They can add key value pairs very quickly as well. And the way that we implemented our hash table was using an array, where we hash the keys to get an array index, and then we store the data at that position. So our hash function is really important. So a good hash function, also a lot of people just say a good hash, should be fast, ideally constant time. And this is talking about hash table, hash map hash functions, not cryptographically secure hash functions. Those have some different rules. But they should be fast. They should distribute keys relatively uniformly. We don't want any sort of conflicts if possible. We want things to be stored as spread out as possible. And we want it to be deterministic. We need to get the exact same output every time with the same input. And then there's two strategies for when we have two keys with the same index. When we hash something, we get the same index in our array. There's at least two that we talked about: separate chaining and linear probing. Separate chaining involves storing them together in a nested structure in the same array index. Linear probing involves looking forward for the next empty slot. And we focused on separate chaining. All right, so that was hash tables. Again, our hash function was very simple. It was not written with the intent to be very useful, really more as an educational demo. But overall, hash tables, hash maps are super, super useful. We use them all the time. Pretty much anytime you need to store key value data, it makes sense to use a hash table. All right.